to this class on distributed power rolling stock. This is being presented to you on IRIMEE's digital learning platform. Distributed power rolling stock refers to electric multiple units and to train sets like train 80. Typically, we are used to seeing loco drawn trains in which we have the loco in the front pulling the train behind it. Now, loco drawn trains are a good time tested concept, but there is a slight problem with this idea. So here you have a locomotive in the front, and this locomotive is trying to pull a really long rake of maybe 24 coaches, or in case of good stock you may have something like 59 wagons. So all the power to pull the train is coming from this locomotive here, and so you can obviously make out that there is going to be a very high amount of force on this coupler between the locomotive and the rolling stock. Okay, so the locomotive needs to be really powerful, and this means that the locomotive has to be an extremely capital intensive and powerful asset. So what happens if the locomotive fails? So if this fails, then there is nothing that you can do with this rake. So you are stuck in midsection until you can arrange for a replacement locomotive. So it's equivalent to putting all your eggs into a single basket. So we obviously need to build in some kind of redundancy into the system. And in fact, experienced traffic officers you may interact with during your probation would tell you that it's always better to run trains in a multiple unit. In fact, many global railways always runs good trains on multiple units, so that if even one of the locomotives does fail, they still can easily clear the section and sometimes even reach the destination. So this is what I have outlined. You need to build in redundancy. You have very high coupler forces at this point. And this last point in which I have spoken about tractive effort. So what I mean is that at this point, you actually need a great deal of friction to be able to pull this rake behind you. But now when you have just one locomotive, you are only using the friction of these 6 axles of the leading locomotive. And so that limits the speed at which you can accelerate it. Now just to explain this concept further, how frequently have you seen a railway line on a mountain or a hill? But very often you find buses and bikes moving up a mountainous road. So what's the reason for that? So the reason for this is that when you buy a car, even if it's a very basic car, then out of these 2 wheels, at least one wheel is driving, that is connected to the engine, and the other one is simply following. Similarly, when you have a bike, the same logic follows. Out of these 2 wheels, at least one of them is driven while the other is just being dragged along. Buses, well, you may have something like, if you have a multi-axle bus, you may have 3 axles, out of which 1 or 2 may be powered. But what happens in case of a train? Just think about it. In the previous slide, I have given you a hint that in a train, a locomotive is trying to pull 24 coaches or 59 wagons. So basically what this means is that 6 axles are actually trying to pull something like 24 into 4, 96 axles, or maybe 59 into 4 axles in case of a goods train, right? So this comes to approximately 240. Okay, so the ratio is really bad. You have something like 6 axles trying to pull about 100 axles, or 6 axles trying to pull about 250 axles. and that means that you really can't navigate this kind of a sharp gradient, and that's why you would find that even the working timetable is so specific about mentioning the ruling gradient. Even a gradient of 1 in 200 or 1 in 300 becomes a big thing for a locomotive. I'm sorry, not 1 in 200 or 1 in 300, but something like 1 in 50 becomes a great deal for a locomotive, but it might be something that a car or a bus can quite easily negotiate. Okay, so one way of overcoming this problem is to go in for teamwork. That is, we go in for greater number of driving sets of wheels. You have more wheels which are driven, so you have more friction to trap into. The coupler forces, instead of being distributed into this single area, are instead distributed across the length of the entire rake. You have some force here, some force here, and then some force here. Advantages of train sets. Now we'll look at some of the commercial aspects of using a train set. These days a lot of people, they stay in the suburbs, and so having a coach or a multiple unit with greater carrying capacity means that you can run more trips between the suburbs and the city. And if you're running on the main line, then a faster speed means that you can actually run a greater frequency of trains. Now the question is that this faster turnaround basically leads to a better asset utilization. I'll just ask you a question. Would you like to have just one train from Delhi to Havana, which runs in the morning, or would you like to have a large number of trains which run frequently throughout the day? I think most of you would opt for the many small hourly trains because we live in an era of mass customization. And those of you who are interested in books, there is this book on the third wave by Alvin Toffler, which actually talks that manufacturing is gradually moving towards a situation of mass manufacture to mass customization. So a train set which actually makes more trips at more convenient times is an example of mass production of a good, moving people in large numbers at the times that they want to do, and that is a good example of mass customization. I'll now move forward and we'll talk about the loco sets or loco trolls or train sets that we have seen in Indian Railways. As an AME, I worked in a diesel shed which had two locomotives, 12169 and 189. These were known as the Medha brothers because they were linked by a distributed power radio system, and they were predominantly used for pulling goods locomotives. But frankly speaking, distributed power for goods rolling stock is a concept which is yet to take off in India, and I hope that with the launching of things like the Anaconda rake, this becomes more and more commonplace. Then we have the famous electric multiple sets of Mumbai, which actually carry the population of the entire city. Then we have the famous Talgo, which had trials in India a few years back. And then there is the famous Trinity. These are some of the pictures. In the first picture, you see three locomotives moving in a ghat section. You obviously need multiple sets to negotiate ghat sections like this. So this is a place where distributed power can come in handy. You could have one set of locomotives in the front and another in the rear. Electric multiple units like the one that you see here, they have powered transportation in cities like Chennai and Mumbai for many years. This is a photograph of the Talgo train which had its trials in India some time back. And then of course we have moved forward from Talgo to our own train set, Trinity. Delve a little bit deeper into this topic. I'll start by posing a question to you. The first question aspect that we need to understand is that we need to have a choice between how do we drive the wheels. Do we drive it through electricity? Do we drive it through diesel? Now, an important concept that all of you need to understand is that it really doesn't matter how you power the train, whether you have a diesel engine or whether you have OHE. At least in the Indian context, the motors which power the axles are always electric. It doesn't happen that a diesel engine directly powers the wheels. It always powers them through a set of electric motors. So now there's a question for you. Why do you think this happens? Is this because of efficiency? Because of a need for speed? Is it because of better torque? Or is it because of less noisy operation of the train? I'll pause for a minute and let you answer this question. The answer to this question is C, that is better torque. As we have seen that in a train, we are actually looking at a mechanism to power about 100 axles using just 6 powered axles, and this means that you have a huge requirement for torque. Okay, so I'll start off by a quiz. Can you recognize the person on the right? I'll give you a moment to think about it. The person on the right is Nikola Tesla. Now, the reason why I show you this photograph is that this battle between direct current and alternating current is quite old. And in fact, 100 years ago, there was an event in American history, which historians refer to as the War of Currents. So this was basically a great debate between Nikola Tesla, the person on the right, and Thomas Alva Edison, the person on the left, over which was a better choice. Should the electricity grid of US be built on alternating current, or should it be built on direct current? Edison was a great supporter of direct current, while Nikola Tesla wanted it to be on alternating current. Eventually, of course, when it comes to the electricity grid, Nikola Tesla, it appears, has won the battle. But this question of AC versus DC is not a very simple one to answer. Alternating current in particular is not very easy to analyze mathematically. Those of you who have studied electrical engineering would have seen graphs like this, requiring the knowledge of something called the phasor angle. And the analysis of alternating current requires extensive knowledge of complex numbers. So it's not a very easy thing to understand or visualize. Direct current, on the other hand, is much simpler. We just have, with time, a single value of current which doesn't change much. Now, I'm not telling you these things to scare you technically, but just to tell you a basic point that alternating current is difficult to understand, visualize, and also difficult to control. And this means that when we talk about the advantages of using a DC motor versus an AC motor, a DC motor has really good starting torque. It's very easy to control and maintain. But its disadvantage is that it requires very heavy maintenance because it has something called carbon brushes, which require regular maintenance. We have locomotives from the Alco family, American Locomotive Company family, like the WDG 3A or WDM 3D. And these locomotives, they need to come to the shed every fortnight. And among the many things that we need to check, one of the things are the carbon brushes. But when it comes to alternating current based motors, you get a very smooth torque. The next advantage is that you get very good regenerative braking. That is, you can electrically brake a rolling stock without the use of friction brakes. It's very useful. In some electric cars, I am told that you never need to change the brake disc. But the problem with this is that you have an extremely complicated closed loop control algorithms. So if any one of you goes on to one of these locomotives like WAG9 or WDG4D, then you would find just behind the driver's console there is a series of electronic cards, And these electronic cards basically they constitute a very complicated and powerful computing system which makes sure that your alternating current based motors continue to function normally. So it takes a great deal of effort to make sure that it functions smoothly. Now this photograph, I just wanted to guess who this person is. I'll just pause for a moment. This person happens to be Jayant Baliga. He's an IIT Chennai alumnus and he's famous as the inventor of the insulated gate bipolar transistor. The IGBT is a technology which actually makes it possible to control AC induction motors. And without these inventions, you would not have electric cars, inverter-based ACs, which are highly energy efficient, freight locomotives like WAG-9 or WDG-4. They save millions of units of electricity each year, and they are in fact powering a green transport revolution across the world. And of course, I have forgotten one small thing in this list. There are train sets like Trinity and metro coaches which run on this wonderful technology. They are highly energy efficient train sets and they also make mass rapid transit possible. So this is a photograph of train 18 and a photograph of one of our metro coaches. I thank you for all your attention, and this completes our basic overview of why we need a train set and what is the basic technology that goes into a train set. Thank you.